All right, so starting here with Chapter P, getting into calculus, first lesson. A lot of this first chapter is going to be a lot of review stuff that we typically hit in like your advanced math classes, your algebra trade classes that we do before this. So it should be a lot of review, or at least hitting on stuff that will translate over into what we all get into with calculus starting next chapter. But before we do that here, let's start here with the kickoff of, let's just plot a graph of y equals x squared minus 2 using the xy chart. So xy chart, simple as that. So we're going to pick, we'll do 5 for this one, but typically all you'll need is at least 2, if not 3, depending on what type of graph it is. So if I do 0 here, so -1, -2, 1, and 2. So starting here with my y. So if I put -2 in, -2 squared would be 4, 4 minus 2 would be 2. -1, -1 squared is 1, 1 minus 2 is -1. 0 squared minus 2, -2. 1 squared, again, be 1 minus 2 is -1. And 2 squared would be 4 minus 2 is 2. So now you have points to plot here. So xy, your coordinate plane. Oh, that is a terrible one. Let's do another one. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Doesn't have to be real complicated, but we're going to go -2, 2, -1, -1, 0, -2, 1, -1, 2, 2. So when we draw in our curves, and away we go. So that's it. Right. Now, with these, we can start looking at, okay, so we have a complicated graph going on here, complicated equation. Well, what would it look like? Well, without even putting in our calculators, doing anything with it, we can figure this out. So we're looking at exponents. We have x to the 4th is the biggest one here. However, there's one more here, means our biggest is x to the 5th, which means it's a 5th degree. Well, odd degree exponents is going to look something like this, where it's going to have an S-shaped type graph. Now, what we did up above here, this would be an even degree or even exponent graph. So x squared, x to the 4th, x to the 6th will do something like this. Now there may be more squiggles in between where there's turns and all that. And we'll get into, or at least you should have covered all that in advanced math, but we'll talk about a little more here about how to do all that. But before we do, or back to where I should say, back to what we're doing, this would be an odd, so any to the 5th, to the 3rd, the 7th, we'll do something like this, all right? So here are some basic graphs that we get into. Intercepts are going to be any point that crosses the x or y axis. So like here we have no x-intercepts, no places where we're going to cross the x. This would be like an even function, so like x squared. However, we have one y-intercept. To be a function, you should only have one y-intercept. Here we could have 3 x-intercepts. So here we have a graph going up, coming back down, going back up. This would be something along the lines of x to the 3rd, x to the 5th. This is where it's odd. But we can have multiple x-intercepts and it's a function. However, again, only one y-intercept. Here now we have 1 x-intercept but 2 y-intercepts. This would not be a function. This is the square root type graph. And then we could have none of anything. Well, this here would be a circle. This is where those are kind of coming from. So, define the x and y intercepts. Well, to start to find the x-intercept, we're going to let y be 0 and we'll solve for x. So we would have x to the third minus 4x equaling 0. And then we'll solve for x. So first thing we do is we look for a common denominator, or not common denominator, a common factor to pull out, which would be x. What would be left is x squared minus 2 equaling 0. So x here we would, or x squared, this would be 4, sorry. X squared minus 4 is the difference of squares. And so what it's going to go to is we're going to have the x and then x plus 2, x minus 2. And each of these are equal to 0. So we set each one equal to 0. So x equals 0, x plus 2 equals 0, x minus 2 equals 0. Well, x equals 0 is already found. Here we would subtract the 2 over, and so x would equal a negative 2. Here we'd add the 2 over, x would equal 2. Now, to find the y-intercept, a little simpler. All we got to do, put 0 in for x. Well, y would equal 0 to the third minus 4 times 0. Well, we're just going to get 0 out. So, in this case, we have 3 x-intercepts, which generally there's going to be one for every degree. So if it's x to the third, generally you're going to have 3 of them, 3 different roots. Now, they won't all be real roots, but you're going to have 3 roots. You might have some imaginary in there, which again we'll get into another time. But that's how you do that. So y equals 0 then for our y-intercept. Now, a lot of times when we're dealing with intercepts, we're going to write them out in ordered pairs. So for an x-intercept, we're going to have 0 for the y, which is why we set it up that way. So we would have the point 0, 0, the point negative 2, 0, and 2, 0. For the y-intercepts, well, technically the x's are 0, which is how we set it up. So it'd be 0, comma, the y-intercept. Now here, the y-intercept was 0. So there you go. Now if it was something different, say y equaled 1 was your intercept, you'd have the point 0, 1. Now, some of those graphs do have symmetry. Now, we didn't graph this here last example, but the one before that. So if I go back to here, back to our kickoff there, that one had symmetry. So that one, we could fold it over the y-axis and it would match up. So we have symmetric about the y, so that y-axis splits it in half. We have symmetric about the x, in which the x-axis splits it in half. Or symmetric about the origin, where our graph then would be rotated 180 degrees and it would match back up. So, tests for symmetry. Well, first you're going to go through and you're going to put a negative x in for every x in the equation. If you get the exact same equation out, then it's going to be symmetric with respect to the y-axis. If we put in a negative y and we get the same thing back out, then it's going to be symmetric about the x. And if we have to put a negative x and a negative y in to get the same thing, it's going to be symmetric about the origin. So, to test this one out, first I'm going to go through and put in a negative x. So y equals 2 to negative x to the third minus a negative x. Well, if we're doing this, negative x to the third would still be negative x to the third, times 2 would make this y equals negative 2x to the third. The minus would make this a plus x. Well, we get the exact opposite here, so this isn't what we want. So no y symmetry. Now, when you do this in your homework, you won't necessarily have to write all of this out, but at least you should go through this in your head and go, okay, if I put a negative x here, what's going to happen? Okay. So if I go to the next one, if I do a negative y, well, technically I would divide by negative 1 to get rid of the negative. So we would have y equals negative 2x to the third plus x. Again, no x symmetry. I'll shorten that up. So the way to check it, the last one to test, is to do negative y equaling, I should technically put that in parentheses here. So 2, now negative x to the third minus negative x. So we're going to put a negative in for both. Well, having a negative y, here we'd have the negative 2x to the third plus x. Well, then if I divide by the negative 1, y would go back to normal. Here they would cancel and you'd have a 2x to the third, and that would make this a minus x, which is what we started with. So this one would have origin symmetry. So those are the three tests you do. Now, if I go and go, oh, wait, this one worked, I have y symmetry, don't keep going and do the other two. Stop there. Once you get one, stop. Now, if we go through and do all of these and it doesn't work, then there's no symmetry whatsoever. It doesn't have to be just one of these three. If none of them work, then it's neither. There's no symmetry. That's also an option. Now, from there you can use the intercepts and the symmetry to sketch the graph and then plot the intercepts to fill in the curve with the symmetry. So like here, if we knew we're, say, symmetric about the y, well, if I'm plotting the points to the right, it should be the same to the left, so it should be symmetric. If it's symmetric about the x, well, then I know, hey, if I curve up this way, then I have to curve back down this way. You know, it'll help you with the figure. Now, it'll also help putting those x and y intercepts to know where you're going to cross and flow through, and that'll kind of help with the shape of the graph as well. Now, we can also find points of intersection where two, say, equations would come together. Well, first you're going to do is you're going to go through and solve both equations for y. So if I have x squared minus y equaling 3, I would add or subtract the x squared over and have negative y equaling 3 minus x squared, and then switch all the signs to have y equals x squared minus 3. So the other one, x minus y equaling 1. Again, subtract the x. So negative y would equal 1 minus x, and then switching all the signs would make this y equals x plus, minus 1. So once you have them both set equal to y, then you're going to set them equal to each other and solve for x. So we would have x squared minus 3 equaling x minus 1. So to solve, we're going to get everything to the same side. So subtract the x, add the 1, subtract x plus 1. So x squared minus x minus 2 would equal 0. And then we're going to factor. So x squared goes to x and x. Negative means one's plus, one's minus. The middle is a negative, so the bigger one has to be the negative. And then x would equal, here it'd be a negative 1, here it'd be 2, because we'd subtract the 1 over after we set equal to 0, and here we'd add the 2 over. So once you get those x values, pick one of those original equations and sub x back in. So I'm going to pick the second one. If I have negative 1 minus y equals 1, I would add 1 over. So negative y would equal 2, so y would equal 2. So my point then would be -1, comma, -2. So I didn't put the mark. The other one I got to test is 2. So 2 minus y equals 1. So minus the 2, -y would equal -1. So y would equal 1. So the point now is 2, comma 1. So what we get up here is the x's. What we get here are the y's. So those form the ordered pairs. So we're going to intersect at this point and at this point, at -1, -2, and at 2, -1 with our two graphs. Now, you could put those graphs in, which you would want to use these here where it's solved for y. You could put them into a graphing calculator and you would be able to see that as well. Now, word problem here. The Mauna Loa, I'm going to say that's how it goes. Anyways, the observatory in Hawaii records the carbon dioxide concentration, Y, in parts per million, in the Earth's atmosphere. The January readings for various years are shown in the following figure. July 1990, these figures were shown to predict the carbon dioxide level for the Earth's atmosphere in the year 2035 using the quadratic model y equals 316.2 plus 0.70t plus 0.018t squared, where t equals 0 represents the year 1960 in the graph. Graph B shows the data from 1980 through 1960, or through 1980 through 2002 modeled by the graph y equals 360.3 plus 1.56t, where t is 0 represents the year 1960. So what was the prediction for the year 2035? What was the prediction for the year 2035 from 1990? Given the new data, does it seem accurate? So what's not on this sheet are these two graphs. So these are the graphs they're talking about, which should be on your notes. And I'll double check to make sure they are. But these are the graphs they're looking at. So in 1990, this is where they thought it was going, and then in 2002, they're like, hey, this is where it's going, and came up with a new graph. So what we're going to do is this. First, we're going to go through, and we're going to set this up to where we're going to use, well, first off, we're looking for the year 2035, and on both of these, t equals 0 is 1960. So how many years past 1960 is 2035? Well, it's 40 to get to 2000 plus another 35. T is going to be 75. So for part A, we're going to use this first equation. So y is going to equal 316.2 plus 0.70. Now our t is 75. So we're going to sub that in. 0.018 75 squared. And this is plus, not equals. Now, go ahead, put that in your calculator, and you should end up with 6, let me write this over, equals 469.95, and our label will be parts per million. So that's the concentration of carbon dioxide. B, we're going to use the second equation. So y equals 306.3 plus 1.56, and we're going to put 75 in for t. Now again, if you put that in your calculator, you will end up with 423.3 parts per million. So, 1990 prediction. It's a little high. Which makes sense, because up here we're using t squared, so it's going to be a quadratic equation. Here we're going to be linear, we're just t. So this is going to be more of a leveled out, which that is what we see here. The first one being x squared, it's curving up, so it's going to, as time goes on, it's going to increase more. Where this is being linear is more of an even, constant growth. And so the curving up, it's going to grow faster, so it should be higher. So that's it. You have just survived your first lesson of calculus. Pat yourself on the back. It is awesome. But until next time, you can either, or next time I see you, I should technically say, if you have any questions, comments, concerns, you can always pan me, email me, send me a message on Google Classroom. Remember, at any point in time, you can always pause this video and write stuff down, or rewind it and watch it again to catch something if you missed it. But until next time, we'll talk to you later.